subscribe now and press the bell icon. Never miss an update.
Hi friends, myself Dr. Darshan Jani, and today we learn about important topic of chemistry, that is rearrangement. Also, don't miss to like and share the video, subscribe the channel Chemistry Online by Dr. Darshan Jani and hit the bell icon to get regular notification for such important videos, right? So today in this session we will discuss about some basic and very important rearrangement. So let me start with our first rearrangement, that is Pinacol-pinacolone rearrangement. So before we start this important rearrangement, we should know about the terminology of rearrangement, that is what is the definition of rearrangement. So term rearrangement can be defined as in any reaction or mechanism when atom or group migrate from one carbon to other either by breaking and or making chemical bond, then this process or phenomena is known as rearrangement. So Pinacol-pinacolone rearrangement can be defined as we all know that every rearrangement having some basic conversion, right? So which type of conversion is carried out in Pinacol-pinacolone rearrangement? So it will convert 1,2-diol into ketone moiety. How this conversion is carried out? Let's see. This conversion is basically carried out in presence of acid. So this rearrangement is also known as acid catalyzed dehydration, right? Now as we can see on the board that first of all in the year 1860 Fittig observed the conversion of 2,3-dimethyl butane 2,3-diol, that is Pinacol, when react in presence of hot 30% H2SO4, that is sulfuric acid, it will be converted into 3,3-dimethyl butane 2-dione, that is Pinacolone. So by this way, in presence of 30% sulfuric acid, this Pinacol will be converted into Pinacolone. Now how this conversion is carried out, let's see with the help of mechanism, right? So in mechanism, here we are taking Pinacol which react in acidic media, as we can see here. So as we all know that every oxygen having lone pair of electron, so in acidic media this lone pair will abstract this proton. So what will happen? One of the hydroxy will be converted into OH2 and this oxygen will get positive charge. So this will becomes the first step of this mechanism. Now in next step, what will happen? This intermediate will undergo loss of water molecule, as we can see here, which is known as dehydration, and we will get carbocation. After formation of this carbocation, methyl group or any substituents on adjacent carbon will shift towards this charged carbon, and this charge will be transferred over the adjacent carbon, and this migration of group from this carbon to this carbon is known as 1,2 shift, which is very important. Now after this migration of group, what will happen? As we discussed earlier, oxygen having lone pair of electrons, so this lone pair will be shifted between this carbon and oxygen to satisfy the charge of carbon, and oxygen will get positive charge, as we can see here. And which step is followed by loss of hydrogen to get our desired product, that is Pinacolone. So by this way we can easily memorize the rearrangement, that is Pinacol-pinacolone rearrangement. Now in every rearrangement there are certain important points, right? So we will go through such rearrangement in details as here we are using symmetric diols, right? So when we are using symmetric diols, doesn't matter which hydroxy group is protonated or leaves or which group is migrate, as we can see here. But in case of unsymmetrical diol, hydroxy group lost should be the one that leaves behind the stable cation, right? So this is very important. And which are the factors which affect the nature or type of product? So as we can see here that stability of carbocation which is formed, then migratory aptitude of the substituents and reaction condition will decide the type or nature of product. Now which are the other compounds which will undergo such type of Pinacol-pinacolone rearrangement? Then such compounds are beta amino alcohol, beta hydroxyaldehyde, allyl alcohol and epoxide. So these are the compound which can easily undergo such type of Pinacol-pinacolone rearrangement. Now as we can see here that in case of 1,2-diol, what will happen? It will undergo dehydration to give carbocation, while in case of beta amino alcohol, what will happen? Carbocation is generated by diazotization, which followed by loss of nitrogen to gives carbocation. As we discussed in this point that this Pinacol-pinacolone rearrangement is very important for other compounds such as beta amino alcohol, in which carbocation is generated by diazotization followed by loss of nitrogen will gives us desired product. So this statement can be easily explained with the help of example, as we are taking here the example of beta amino alcohol which will react with HNO2 nitrous acid, right? So what will happen? This NH2 group will be converted into diazonium group. Now this intermediate followed loss of nitrogen to gives carbocation, as we can see here. Again the phenyl group on adjacent carbon will shifted to satisfy the charge of carbon, and this adjacent carbon will get positive charge, and this process or this migration is known as 1,2 shift, as we discussed in earlier example of 1,2-diol. Now as we all know that the lone pair of oxygen, right, this will shifted between this carbon and oxygen to satisfy the charge of carbon, and oxygen will get positive charge, and this positively charged oxygen undergo loss of hydrogen to gives our desired product, right? So by this way we can also carried out Pinacol-pinacolone rearrangement in case of beta amino alcohol. And at the end of this reaction or rearrangement, as we can see the important part application of this rearrangement. So this can be defined as in case of 1,2-diol, when we carried out reaction of this 1,2-diol in presence of acidic media, in presence of iodine, it will be converted into ketone, and this rearrangement is also useful for the synthesis of spiro compound, as we can see here. So both this type of diol can undergo such rearrangement in acidic media to give such type of spiro compound. So by this way we can easily memorize Pinacol-pinacolone rearrangement. So friends, next important rearrangement is Wagner-Meerwein rearrangement. It basically involves the rearrangement of carbocation, right? It basically involves rearrangement of carbocation as intermediate. So this statement can be easily explained with the help of example, as we can see here in example that in case of 3,3-dimethyl 1-butene, right, as we all know that according to the rules of IUPAC nomenclature, right, as we start numbering from this carbon, it will becomes 1, 2, 3, 3,3-dimethyl 1-butene. When this compound will undergo addition of HCl, so it will gives two types of product, whether 2-chloro-2,3-dimethyl-butane and 2-chloro-3,3-dimethyl-butane. Out of these two product, this one, that is 2-chloro-2,3-dimethyl-butane, will becomes a rearranged product, while this will becomes not rearranged product, right? So this can be better explained with the help of one more example as well as mechanism. How? Let's see. So basically, with formation of carbocation, it also involves the migration of alkyl group with its pair of electron, right? So these are the two important points in Wagner-Meerwein rearrangement. So this can be better explained with the help of one more example, as we can see here, that neopentyl alcohol, right, when it will undergo reaction with HBr in presence of H2O, then this will gives 2-bromo-2-methyl-butane as a arranged product, or we can also say that a rearranged product, right? So how this conversion is carried out can be easily explained with the help of mechanism. So here in mechanism, we can say that we can see that in case of neopentyl iodide, what will happen when it will undergo hydrolysis? So ionization will give primary carbocation as a product, or we can also say that the iodide, right, is a better leaving group and it will give primary carbocation as a product, whether intermediate, right? Then this intermediate will undergo 1,2 shift or 1,2 alkyl shift, right? So this will give tertiary carbocation as a product. As we all know that tertiary carbocation is more stable compared to primary one, then this tertiary carbocation will undergo further reaction with H2O to give our desired rearranged product, that is 2-methyl-2-butanol. Now friends, generation of carbocation, as we see here that it involves the formation of carbocation intermediate. So this formation of carbocation intermediate can be carried out by 3 or 4 ways, as we can see here that a loss of H2O from protonated alcohol, right? So this is the first way by which we can synthesize a carbocation. Then also we know that loss of nitrogen from diazonium ion, so it will also gives a carbocation intermediate. Again, loss of halide from alkyl halide, right? And last but not the least, that protonation of alkene again produce carbocation intermediate, but it will follows the Markovnikov rule. So friends, as we discuss various way for the formation of carbocation in Wagner-Meerwein rearrangement, so there are 2 ways mainly, that is loss of halogen from alkyl halide and protonation of alkene. So these are the 2 ways by which we can also synthesize or generate carbocation. So this 2 way can be further explained with the help of example, as we can see on the board, that when alkyl halide undergo loss of halogen, or when we carried out protonation of alkene, right? Also we know that this protonation of alkene follows the Markovnikov rule. And what is Markovnikov rule? As we discussed earlier, we already studied in earlier standard that when you are carried out addition of unsymmetrical reagent to the unsymmetrical alkene, then proton will be added to the least substituted carbon, right? So this is the Markovnikov rule. So by this way, either from alkyl halide or from alkene, we can synthesize carbocation. Then after formation of this intermediate, what will carried out? It will undergo 1,2 shift to gives from a primary carbocation to more stable secondary carbocation. After formation of this secondary carbocation, or after 1,2 alkyl shift, what will happen? There are two possibilities. Either it will undergo loss of hydrogen or H plus ion to gives these two different type of alkene, as hydrogen can remove either from this carbon to gives this alkene, or it may lose hydrogen from this carbon to gives this alkene, or this intermediate or carbocation may undergo substitution of Y, right, any nucleophile to gives this product. So by this way we can easily define Wagner-Meerwein rearrangement. Also there are certain special cases. For example, as we can see here, that acid catalyzed dehydration of neopentyl alcohol. So as we can see on the board, that neopentyl alcohol when undergo acid catalyzed dehydration, right? So when we add acid, what will happen? This will becomes OH2, O will get positive charge. So after loss of H2O, this will gives primary cation, which will undergo 1,2 alkyl shift to gives tertiary cation, right, which is more stable as we know, right, and this will undergo loss of H plus to gives our desired alkene, that is 2-methyl 2-butene as a product. Now as we discuss here the acid catalyzed dehydration, so there is one more case in Wagner-Meerwein, as alicyclic compound lead to expansion or contraction of rings. So this can be better explained with the help of this example of 2,2-dimethyl cyclohexanol, as we can see here, right? When we carried out addition of hydrogen, so it may undergo 1,2-dimethyl cyclohexene after expansion, or it may gives 1-isopropyl cyclopentene by contraction of rings. So by this way we can say that in case of alicyclic compound, when we carried out Wagner-Meerwein rearrangement, it will leads to either expansion or contraction of ring. Right now, if we if we discuss about migratory aptitude, so as we all know that aryl having more migratory aptitude compared to alkyl as well as proton. As we can see here that aryl group have greater aptitude than alkyl group or hydrogen for migration, right? And particularly in case of aryl, what will happen? When there is electron donating group in aryl, it will increase the rate of migration, while electron withdrawing group will decrease the rate of migration, right? So this will becomes the migratory aptitude when substituted aryl is there in case of Wagner-Meerwein. And in last, as we discuss, very important part, application, right? So as we can see here, 9-fluoroocene carbinol, when it will undergo Wagner-Meerwein in acidic media, it will undergo dehydration to give such type of intermediate, and after certain rearrangement, hydrogen from this position loss in form of H plus, this bonding pair will be shifted between these two carbon to give double bond, and we will get phenanthrene as our desired product. So by this way we can easily memorize very important Wagner-Meerwein rearrangement. So friends, Next important rearrangement is Favorskii rearrangement. As we can see that on the board, which type of conversion is basically carried out in Favorskii rearrangement. So as we can see that alpha haloketone will be converted into acid, or we can say that ester. How this conversion is carried out, let's see here on the board with reaction that as we can see, alpha haloketones when react with sodium alkoxide, it will be converted into respective ester or acid, right? So when we discuss about cyclic ketones, then as we can see from the example that cyclic ketones undergo ring contraction. How this is carried out, as we can see in example that cyclohexanone when react with Br2 in acetic acid, so it will convert into alpha haloketone, right? When it react with sodium methoxide, it will be converted into methyl cyclopentane carboxylate. So with this example we can say that when cyclic ketones undergo Favorskii rearrangement, it will give ring contraction. So how this conversion is basically carried out can be easily explained with the help of mechanism. So here we are taking the example of alpha haloketone when it react with either alcohol or sodium alkoxide. As we know that alkoxy is a strong base, right? So it will abstract proton, and this bonding pair is shifted over carbon to gives carbanion intermediate. So after formation of this carbanion intermediate, it will undergo loss of chloride and converted into reactive cyclopropanone intermediate, as we can see that. So after formation of this reactive cyclopropanone intermediate, what will happen? The another molecule of alkoxy will attack over this carbonyl carbon. This bonding pair will be shifted over oxygen and we get a negative charge, as we can see in next step. Now after formation of this alkoxy attack, what will happen? This negative charge of oxygen will be shifted between this carbon and oxygen, and this bond will be break, and this bonding pair will be shifted over carbon to get carbanion intermediate, and after this it will abstract proton from alcohol to gives our desired product, that is ester, as we can see that. Now this mechanism is also supported by synthesis of same ester from isomeric haloketones. So how this carried out, or we can also say that how this mechanism can be proved with the help of isomeric haloketone. So here we are taking example of isomeric haloketone. So from both this type of ketone we will get such type of substituted cyclopropanone intermediate, which will undergo attack by alkoxy over this carbonyl. This bonding pair will be shifted over oxygen and we will get such type of intermediate. After formation of this intermediate, there are two possibilities, right? Either this bonding pair over oxygen is shifted between carbon and oxygen, and this bonding pair will be shifted over carbon and we will get carbanion like this, and this is the first way. And the another possibility that if this bonding pair will be shifted between carbon and oxygen, whether this bond will take place, undergo breaking, right? And this bonding pair will be shifted over carbon and we will get such type of intermediate or carbanion. So there are two possibilities, but out of these two possibilities, A and B, the B is less stable, as we can see that in case of A, this negative charge or lone pair is delocalized over phenyl or benzene ring, right? So this is more stable and we will get the same ester. As we can see that also we can define the application part or special case in case of Favorskii as alpha alpha dihalooketones, right? Alpha alpha dihalooketones when undergo reaction with sodium alkoxide in ether, it will gives alpha beta unsaturated ester as a product. So by this way we can easily memorize very important rearrangement, that is Favorskii rearrangement. So friends, next and last important rearrangement is Beckmann rearrangement. So as we discussed earlier, which type of basic conversion is carried out in Beckmann rearrangement. So as we can see on the board that oxime will be converted into N substituted amide in presence of acidic rearrangement, then this rearrangement is known as Beckmann rearrangement. So which are such acidic reagents can be used to convert this oxime to N substituted amide? Let's see on the board. As we can see here that PCl5, phosphorus pentachloride, then concentrated H2SO4, that is sulfuric acid, polyphosphoric acid, thionyl chloride, silica. So such type of acidic reagent are mainly used to convert oxime to N substituted amide, right? So with example in reaction we can see that here oxime will be converted into benzanilide in presence of acidic reagent such as H plus or PCl5, that is phosphorus pentachloride. So how this rearrangement is carried out can be easily explained with the help of mechanism. As we can see here that when oxime react in acidic media, what will happen? As we all know that oxygen having lone pair of electron, so it will abstract proton and gives OH2 plus. Clear? Then in next step what will happen? This OH2 plus will remove by taking this bonding pair and this alkyl group with bonding pair of electrons shifted towards the nitrogen, right? So after loss of water molecule we will get such type of electron deficient carbocation. Now this carbocation will undergo attack with water molecule having oxygen having lone pair of electron, which will satisfy the charge of carbon, and we will get such type of intermediate. Now this intermediate will undergo loss of hydrogen to gives OH, and from this intermediate this hydrogen will loss in form of H plus. This bonding pair will be shifted between carbon and oxygen. This bonding pair will be shifted over nitrogen and nitrogen will get negative charge, and this proton may attach this nitrogen to gives our desired product, that is N substituted amide. So friends, from this mechanism we can say that the role of acidic reagent is to convert living group into better living group, right? So with the help of this acidic reagent we can easily convert this hydroxyl into better living group to produce such type of electron deficient carbocation. So there is one more example in which we are using PCl5, phosphorus pentachloride. So how it will react? As we can see here that oxime will react with PCl5, this hydrogen and one of the chlorine will remove in form of HCl, and we will get such type of intermediate. After formation of this intermediate, this alkyl group, as we discussed earlier, this alkyl group with bonding pair of electrons shifted towards the nitrogen, this bonding pair will be shifted between this oxygen and phosphorus, and Cl will loss. So after loss of chloride and phosphorus oxytrichloride, that is POCl3, we will get the same intermediate. Okay, then it will attack by Cl, and reaction with H2O will replace this Cl with OH, and after rearrangement we will get our desired product, that is N substituted amide. When in case of chiral substituents, chiral group will migrate with retention of configuration, and at the end, as we can see that in application part, right, there are two important application. As we can see here, synthesis of caprolactam from cyclohexanone oxime can be easily carried out with the help of Beckmann rearrangement, and in this reaction, as this ketone group, when it react with hydroxylamine, it will be converted into oxime, and then after reaction with PCl5, this carbonyl will be converted into N substituted amide. So by this way we can easily define very important fourth rearrangement, that is Beckmann rearrangement. So friends, don't miss to like and share the video, subscribe the channel Chemistry Online by Dr. Darshan Jani, and hit the bell icon to get a regular notification for such important videos. Thank you very much.